Sure.
Perfect. So it's a great pleasure to have today Oliver Janzer, right, who many of you know because he was for quite a while in Zurich. And Oliver will talk about edge-disjoint cycles with the same vertex set, which is a very cool problem of Erdős, on which he and his co-author make a very nice progress. Please, Oliver.
Thanks, Benny, for the invitation. It's a pleasure to speak here. And I'll be presenting joint work with Debsoumya Chakraborti, Abhishek, Methuku, and Richard Montgomery. And indeed, it will be about edge-disjoint cycles with the same vertex set. So in general, finding cycles in graphs, particularly finding cycles with various extra properties in graphs which have enough edges is a central problem in graph theory, and often we want to determine how many edges you need to find a certain structure. And if you don't put any restriction on the cycle, you just want an arbitrary cycle, then obviously you need n edges in an n-vertex graph. But what if you want to control its length? Then the problem becomes more difficult. And if you want a cycle of a fixed length, a given length t, the problem is the Turan problem, and this number is known as the Turan number of cycle of length t, which is known when t is odd. Extremal construction is the complete bipartite graph. However, when t is even, then this is an important and notoriously difficult open problem. So there have been some tools developed recently for finding cycles with controlled length. It's not really going to give you a cycle of fixed length, but nevertheless you can control the length in some way, and these tools applies for sparse graphs as well. So Liu and Montgomery made some very nice progress, and among other results, they proved that there exists a constant C, such that every graph with at least C times n edges contains a cycle whose length is a power of 2, which resolved a conjecture of Erdős from 1984. So I will, from now on, I'll not say the graph has n vertices. I'll just, whenever you see an n, it's the number of vertices in the graph. Okay, today I'll talk about a related problem. It's natural to ask, what if you want to find two cycles with certain properties? And in 1975, Erdős proposed following three questions about this topic. And the first one is, what's the maximum number of edges you can have without containing two edge-disjoint nested cycles? And the second question is, what if you want to find two edge-disjoint nested cycles with no geometric crossings? I'll explain in a moment what I mean by that. And the third question will be the main topic of today's talk. How many edges can you have in a graph without containing two edge-disjoint cycles with the same vertex set? So before I turn to the main topic, let me just briefly talk about the first two problems. So what do we mean by nested cycles? We mean that the vertex sets are nested sequence. Here, obviously, I don't see I doesn't mean a cycle of length I, but it's just an index for the ith cycle. So one thing I would like to point out is that two cycles on the same vertex set are trivially also nested. So, well, any bound on the third problem implies the same bound on the first problem. In particular, finding two edge-disjoint cycles with exactly the same vertex set is more difficult than finding two nested cycles. Okay, so just to have a picture for the first two problems, the first picture shows two edge-disjoint nested cycle. You can see that C2's vertex set is a subset of C1's vertex set, but it does have crossings on the picture. And the second picture shows two nested cycles with no crossings. So that's what the first two problems mean. And let me review the progress on the first two problems. They've both been resolved now. So in 1978, Bollobás resolved the first problem by proving that linearly many edges are enough to find two edge disjoint cycles, which are nested. And this was extended to the case of K nested cycles in 1996 by Chen, Erdős, and Staton. And the second problem of Erdős was resolved recently in 2022 by Fernandez, Kim, and Liu. Again, they proved that linearly many edges are enough to find two edge disjoint nested cycles with no crossings. Despite these advances, the third problem remained open, and these results do not say anything about the third problem. They don't give any bound on that. So let me restate for your convenience this problem. What's the maximum number of edges that the graph can have without containing two edge disjoint cycles with the same vertex set? That's going to be the problem I'll talk about today. And this problem has connections to many other important problems, and therefore has been reiterated in various contexts by several authors. So first, it was reiterated by Bollobás in his book on extremal graph theory. Then was also reiterated by Pyber, Rödl, and Szemerédi in 1995 in the context of the Erdős-Sayer problem. And the connection here is that if you have two edge disjoint cycles on the same vertex set, then the union of those two cycles is a 4 regular graph. And of course, Erdős-Sayer problem asks for the maximum number of edges you can have without containing an R regular graph. So that's the connection. It was also reiterated by Chen, Erdős, and Staton in 1996 in the context of cycles with many chords. So what do I mean by that? These authors asked how many edges a graph can have without containing a cycle with at least as many chords as it has vertices. So you want a cycle, but you want a bit more than that. You want, if you give me a K cycle, you want also K, at least K chords in it. And the connection here is that if you have two edge disjoint cycles on the same vertex set, then you can view the second edges of the second cycle as chords of the first cycle, and you obviously get as many chords here this way as number of vertices in your first cycle. So certainly two cycles with the same vertex set give you this cycles with many chords. And this problem of Chen, Erdős, and Staton was asymptotically resolved recently by Dragonich, Methuku, Munya-Correa, and Sudakov. They showed that n times polylog n edges are enough to find a cycle with many chords. So what are the known bounds for our problem, for this the problem of finding two edge disjoint cycles with the same vertex set? Well, there's an important difference compared to the previous problems of Erdős about nested cycles. Here the answer is not linear. So answer going to be superlinear, and that's because of the connection to the Erdős-Sayer problem. So Pyber, Rödl, and Szemerédi constructed a famous graph with superlinear number of edges and log n edges, which do not contain any R regular subgraph for any R at least 3. And in particular, they don't contain 4 regular subgraphs either. So they cannot contain two edge disjoint cycles with the same vertex set. So this is the best known lower bound n log n. And what kind of upper bounds do we have? not a lot. So Chen, Erdős, and Staton observed that K44 contains two edge-disjoint cycles on the same vertex set, and this gives an upper bound of n⁴ using the best known bound for the two-run number of K44. And more generally, you can use any graph H, which contains two edge-disjoint Hamilton cycles, and then that graph, the two-run number of that graph is going to be an upper bound. However, this approach will not get you very, very far, because if you have a graph which contains two edge-disjoint Hamilton cycles, then necessarily it has minimum degree at least 4. And by the probabilistic deletion method, its two-run number is going to be at least n⁵ plus epsilon. And a slightly better bound was observed at a second Armenian workshop on graphs and was communicated to us privately. There it was noted that the two blob of any cycle contains two edge-disjoint Hamilton cycles. And the cycle doesn't have to have bounded length. So it doesn't have to be a fixed length cycle. So you can use a result of mine that gives you a bound on the number of edges that you need to find the two blob of an arbitrary cycle. And that's n⁵ plus literally 1. So this is an upper bound for our problem as well, and this was the best known upper bound, actually. So what I would like to talk about is that we asymptotically resolve the problem of Erdős in a stronger form, because we are actually able to find not just two cycles, but an arbitrary constant number of cycles on the same vertex set. And we only need polylog n times polylog n edges. So this is the main result that I'll talk about today. The exponent does not depend on k, actually. So it's an absolute constant power of log n. And of course, as I pointed out earlier, this implies the results of Dragonich, Methuku, Munya-Correa, and Sudakov on cycles with many chords, although with a different power of log n. Okay, so let me give you first just a very brief overview of the proof, just mentioning some of the tools, then I'll get into the details. So our proof uses several tools, such as robust sublinear expanders, absorption, and cool new ingredient, which is a novel regularization lemma, which is of independent interest and has other applications. So what I'll do in this talk is I'll sketch the proof, restricting myself to 2 cycles. So I'll not talk about k cycles. The proof is very similar for k cycles, but it's just easier to give the proof for 2 cycles. So I'll give the proof, I'll sketch the proof under the assumption that our host graph is a regular expander. Of course, in general, your host graph might not be a regular expander. You can always find an expander, but it might not be regular. Then I will introduce our new regularization tool, which somehow doesn't destroy the expansion property. So there are tools for regularizing graphs, but the known tools will not respect the expander. So if you use them, you lose the expansion property. Our new tool has this nice feature that it does not destroy the expansion property. So it can actually reduce the problem to this case of having a regular expander. And then I'll conclude the talk by mentioning some other applications of our new regularization tool. Okay, so let me start with the proof. Again, we are going to prove the result first under the assumption that the host graph is a regular expander. So what kind of expander are we talking about here? Of course, there are many different notions of expansion. We'll talk about sublinear expanders here. Like many recent important advances about cycles and graphs, our proof does use sublinear expanders, and we use a notion of robust sublinear expansion. I think in this form, this notion was introduced by Erdős and Montgomery in their paper on the Erdős-Galai problem. We call a graph an epsilon expander if every vertex set that's not already very large does expand, even if you need to avoid a certain subset of the edges. Now, how large the subset of the edges you need to avoid depends on first S, which is the strength of the expander. So the higher S is, the better expander it is, the more edges you can forbid to use. But also the number of edges that you forbid to use will also depend on the size of the set. Kind of has to scale with the size of the set. Otherwise, for small sets, you can kill the expansion by just deleting every edge incident to that small set. So it's a natural thing that the number of edges scales with the size of the set that you want to say expands. And the expansion is, as the name suggests, sublinear, so it's not constant times u, but a constant u over log squared. Epsilon is a fairly unimportant parameter. You should just think of it as a constant. Now, importantly, it was shown that these expanders exist in any graph. And you can take S to be almost as large as the degree, average degree. Here and below G is the average degree of the graph G. Now, clearly you can't have S bigger than the average degree because, as I said before, if you delete every edge incident to a set, then the set will definitely not expand. So you can only delete roughly the degree many edges per vertex. So you can't hope to find an expander with S higher than dg, but you can, as they showed, find an expander where S is close to dg. And it is not actually hard to show that, in addition, you can achieve some sort of regularity. But it's a relatively weak sense of regularity, at least for our purposes, it will not be sufficient. You can easily achieve that your expander is also 18 almost regular, by which I mean that the maximum degree is at most 18 times the minimum degree. As we will see in the proof, I'll convince you that this regularity is not enough for our proof to go through. So you'll need a more regular expander than this. Okay, so now assume that G is regular or extremely close to being regular, and you have an expander with S roughly the average degree of G. Now, this is going to be a fairly important notion. We call a set nice informally if one can connect many pairs of vertices using short vertex disjoint paths that go through V. So we are looking for paths with internal vertices in V. And V is nice if you can find many vertex disjoint paths connecting a fixed collection of pairs of vertices. And the formal definition, I mean, you want to quantify how nice a set is, and it's going to be called mu nice if for every sequence of not necessarily distinct vertices outside of your set, all you need is that every vertex in V sends at most mu edges to this multiset. So your sequence x1, xr, y1, yr gives a multiset, and you want every vertex in V to have relatively few neighbors, less than mu neighbors in that sequence. And if that holds, and if your set is nice, you can connect xi to yi for every I through this nice set V with short paths. And the way we will use it is, we'll find some structure in a graph, which is maybe not a cycle, not quite a cycle, but it's a cycle with a few edges missing in it. And then the missing edges correspond to pairs that you want to connect, and you will connect those pairs through this nice set V using short paths.
And
use nice sets. Sorry.
Yeah, we should think about mu kind of proportional to the degree, much smaller than the degree. Obviously, it cannot.
You should think about mu. Yeah, it's going to have to be a bit big, well, if it's as big as the degree, then you're very happy, but we will achieve mu nice sets with mu relatively close to the degree. So yeah, mu is it's going to be a bit smaller than the degree, but not by much. Yeah, that's probably the best way to think about it. It's a bit smaller than the degree, but not by much. But it's going to be relatively large, yes. Thank you. Yeah, please ask questions. And well, the important thing for us will be that random subsets of the vertex set in expanders are nice. So we will use these sets V that we use in our proof randomly, and we show that they are nice. So a similar result was proved by Bucic and Montgomery, but we need a bit stronger, quantitatively stronger statements. So we can't quite use their results. And we prove this. We prove this this lemma that if you have a p-random set, then you will be mu nice for mu roughly p to the 9 times s. So now getting back to Benny's question, so s was roughly about the degree. So now mu is going to be roughly p to the 9 times the degree. So obviously, the smaller V is, the harder it is to connect through V. So it kind of has to scale with P, and it scales with this reasonable way, in this reasonable way, as P to the 9 times S. So that's what we prove. And in our proof, P will be some polylog, 1 over some constant power of polylog usually. And well, informal corollary that we'll kind of rely on is that if you have a random subset of your vertex set and you have another set outside of your random subset, that's significantly smaller than V and is in some way random-like. The random-like we only need in the sense that degrees to it are a bit like if it was a random set. I mean, the lemma, this notion of niceness cares about the degrees to the pairs that you want to connect. So what we need about U is that the degrees to it are random-like. So if this U is random-like, then we can connect an arbitrary collection of pairs in U through this random set V using short vertex disjoint paths, as long as each vertex appears at most a constant number of times in the collection. So well, in this proof, we'll never want to connect a given vertex to a million other vertices, because at the end of the day, we want 2 cycles. So we would never need, we'd never really need more than degree 4 at each vertex. So we'll only really connect any given vertex to, say, 4 other vertices. So it's certainly going to be satisfied that each vertex appears at most a constant number of times in the collection of pairs and that we want to connect. Okay.
Maybe one
So
more
now,
question.
sorry, yes.
Oliver, one more question. So potentially this can go, because in a random set, every vertex, if you graph at logarithmic degree, would have roughly log n neighbors, right? Could you increase this number of pairs you connect almost to up to degree, to some function of the degree, or there is some natural bottleneck why it will stay constant?
Oh, the number of pairs you connect is
How
going to
many
be
pairs
more than a
every
constant.
vertex participates, right?
Oh, you can increase it. You can increase it. You can increase it to log. You can increase it. You can increase it to even a very large number. But then what you can't do is to connect each vertex to a very large number of other vertices by very large number of this. I mean, you can connect as many as so that the multiset is mu nice. So all you need is that if you want to connect a given vertex to, say, k other vertices, then in the multiset it will appear with multiplicity k. So then that will contribute to the degree to the multiset. But you can absolutely, you can connect to a large number of other vertices. There's no problem at all there. So how do we construct the cycles? Let me talk about that. So most of the vertices in the cycle and most of the edges in the cycle will come from matchings glued together. So I'll draw a picture on the next slide, but we'll take a number of matchings and we'll glue them together. And what you end up with is a linear forest with relatively small number of components. So it will be a collection of long vertex disjoint paths. And that's not a cycle, of course. So you will need a reservoir set through which you can connect the endpoints of the paths in the linear forest. And if you have a bunch of paths and you connect each endpoint of one path to an endpoint of another path, you can do it in a way that it closes a cycle. So you kind of close a linear forest into a cycle. And you close it through this reservoir set R. R will be chosen as a large random set. So it is going to be nice according to our previous result. So you can indeed use R to connect many pairs of vertices. But not every vertex in the reservoir will be needed in this procedure. Some vertices will not be used to connect paths. And that's a bit of a problem because at the end of the day, we need two cycles with exact same vertex set. So the only natural way to ensure it is that both cycles will use the entirety of R. So we'll need to use the entirety of R in our vertex set. And therefore, we need some absorption. We need an absorber to absorb the unused vertices in R. So let me illustrate how we get the cycle now. This picture will appear later in the talk and it will make more sense, hopefully, but it already has some features that we understand now. So let me start with R, this gray area in the middle, it's the reservoir. You can see that there are these red and blue paths going through it, which are used to connect certain pairs of the vertices, And the top part is the union of matchings parts. So you have these 5 blobs on the top, and between consecutive blobs, you have matchings, which are not perfect matchings, but close. So they imagine them as almost perfect matchings. Then since they're not perfect matchings, you need some missing edges, like between the second and the third blob, there is a missing edge. There should be an edge there, ideally, but there isn't. So you can replace that edge by these red paths through the reservoir. Same between the 4th and the 5th cycle. And also you need to close the cycle. So you need to connect the first blob to the last blob. And you do that through the reservoir again using these blue paths. So if you combine the blue paths and the red paths with the matching, then you basically get a cycle, but it might not use all the vertices of R. So you need some absorbing structure, and that I'll explain it, how you get it, but that's the green part here. It's a chain of absorbers, which is for any given cycle, it's a path. So this green thing is a path that can be used to absorb any vertex in R. So if you accept that the green thing is a path, then this whole picture is a cycle. So okay, let me talk about the absorption a bit. So we say that a gadget is an absorber for some vertex R and connects vertices X and Y if it contains two paths between X and Y, which differ only in R. So one has some internal vertex set S, the other has internal vertex set S union R. For example, in this silly picture, I drew a gadget that can be used to absorb R and connects X and Y, because you have a path between X and Y which doesn't use R, and also a path which uses R. Now, there is an issue here, actually, which is that these gadgets will not exist. As the way I define this absorber, they don't even exist in bipartite graphs. Because if you have a bipartite graph, then between any pair of vertices X and Y, you either have only even length paths or only odd length paths. So you can't have both parities. So you can't actually absorb any vertex. And your graph can absolutely be bipartite. You start with, you have a very sparse graph with n polylog energies, so it could easily be bipartite. So this is a problem, and will actually, in reality, absorb vertices in pairs. So this is, so the way I define absorber is not the absorber we'll use, and certainly the gadget will not look like that 5-vertex gadget on this picture. But to make the proof easier to follow, I'll just ignore this issue, and I'll pretend that absorbers for single vertices exist in our graph.
Can I ask a question then?
Yes, please.
So is the absorber this vertex at S, or is it just a, what is a gadget?
It's a subgraph. It's like
a subgraph. Okay.
Yeah, it's a subgraph basically.
With vertex at S, or am I understanding?
Well, the vertex at S is your choice. It's not a something fixed, so we'll not care what a vertex set exactly is. But I think the gadget, we think of it as a subgraph which contains both a path through X and Y and also a path through X and Y with the same vertices, but also R, so just with one more vertex. And all we'll care about is that these absorbers are vertex disjoint. So, well, they'll be internally vertex disjoint. So all these S bits are disjoint, but the X's and Y's will overlap, as we'll see in one moment. Okay, so how do you build this chain of absorbers? So I've already told you that R is a random set, large random set, and now we take another larger random set, which is U. And in U, we find a random subset of size R plus 1. So let me enumerate vertices of R as R1 to Rs and vertices of X as X1 to Xs plus 1. And now for each vertex in R, we will find two absorbers, two absorbers. One will be used in the first cycle, and one will be used in the second cycle. And I'll denote them by EBS1 and EBS2. And I should point out that I'm not yet specifying which one is used in which cycle. I'm not saying that EBS1 is going to be used in the first cycle. I'll tell you later how to allocate that. But I'll need two absorbers because I have to construct two cycles, and I need to construct two edge-disjoint cycles. But both absorbers will be very similar in the sense that they can be used to absorb the same vertex, and they connect the same pair. So they both go from xi to xi plus 1. And this gives a chain of pairs of absorbers. And this is the picture you should keep in mind. So you have these x1, x2, x3, ... just some fixed vertices. And between consecutive xi's, you have two absorbers. You have two choices. And essentially, each absorber is a path. I mean, it's not strictly speaking a path, but if you decide not to absorb the vertex, it's a path. And if you decide to absorb the vertex, it's still a path, just a different path. So you should definitely think of them as paths. But
just
yes.
Question about it. So there's these pairs of absorbers.
Yes.
Can we both decide not to use R1, or is it that one of them will use R1 and the other is not? So
very good question. Very good question. So it's not that one of them will use R1 and the other one will not. But rather, and hopefully this will become clear in the next slide, one absorber will be used in the first cycle and the other one will be used in the second cycle. So let's swap to the next slide. So you have an allocation. So the red one are the absorbers will be using for the first cycle, and the green ones are used for the second cycle. Then at this point, still, I have not decided yet if I'm actually going to absorb R1 and R2. So it's still undecided. I decide first in some way that I'll explain how to allocate absorbers to the two cycles. But at this point, I still not decided if I'm going to actually absorb R1 and R2. But I have the possibility to absorb. Okay, very good, thank you. So what I need about this absorber is just that their vertex is joined. I mean, obviously, they're not completely vertex disjoint because they overlap on these xi's, but otherwise, whatever looks like a disjoint, whatever looks like distinct vertices on this picture are distinct. You can find such a structure using the property that U is a nice set and R is a random set. I'll not explain how exactly. And now, how do we build? So now we have a chain of pairs of absorbers, but we need a chain of single absorbers for each vertex. And I do some allocation, which I can already tell you will be done randomly, and it's crucial that it's done randomly. So the red ones will be used in the first cycle. The green ones will be used in the second cycle. And then for each cycle, we get a chain of absorbers, which is a path. It's just a path. So from x1 to x5, we get a nice path. And this is what I meant in this picture by the chain of absorbers. Now you can see that it actually is a path for each of the two cycles. So this is how one of the two cycles will look like. This picture tells you how one of the two cycles looks like. Okay, so what is the issue here? I mean, what is the main task? Well, the problem is that the first cycle will use the red absorbers, fine, but both cycles need to use the same vertex set. So actually, what will you do with the green absorbers? The first cycle does not use the green absorbers, but it must use those vertices somewhere. So it must include the vertices in the green absorbers. So that's the task that it's the main task we need to resolve. So you have UAbs, the set of all vertices used in all absorbers. And of them, there are the vertices that are used in the jth cycle, which I denote by ABs J. So UAbs naturally splits into two parts, UAbs 1 and UAbs 2. And the first cycle does naturally use UAbs 1, but doesn't at the moment use UAbs 2. So we need to find a way to incorporate the vertices in UAbs 2 into the first cycle. And this is where those matching stuff will come in. So what we'll do is find a structure on the induced subgraph of G on the set UAbs 2 that is essentially a Hamilton cycle, but not quite a Hamilton cycle. It will be a Hamilton cycle with a few edges missing. If only a few edges are missing, that's fine, because we can use the reservoir to correct it, to create an actual cycle. So we'll need something we need a spanning structure that is not exactly a cycle, but a linear forest, but only a few edges are missing. And we can do this under the assumption that this induced subgraph is nearly regular. And I'll explain how it's quite simple. If you have a nearly regular graph, how do you find an almost Hamilton cycle in it? And what I would like to emphasize, I'm looking for a spanning, a genuinely spanning thing, which is a linear forest with few edges missing. What you do is you partition your vertex set randomly to a large-ish number of parts, and between consecutive pairs, the graph that you get is, since these sets are random, the bipartite graphs that you get are all nearly regular. So you can find almost perfect matchings between them by whatever Wising's theorem. And if you put all these matchings together, then you get the desired structure, a Hamilton cycle with a few edges missing. And this is the picture. So you have a bunch of these blobs, and between consecutive blobs, you have almost perfect matchings. The dashed lines represent edges that are missing. They're not there. Now, if you add the dashed lines, you get something that's still not a Hamilton cycle, actually. But if you now add the dotted lines connecting vertices in the last blob and vertices in the first blob, then you get a Hamilton cycle or path. So you need only to add these dashed edges and the dotted edges to create a Hamilton cycle. And that's a relatively small number of pairs because the matchings are almost perfect, so the dashed edges are relatively rare. And the dotted, why are the dotted edges rare? It's because T was pretty large. So, I mean, you only need how many dotted edges? Basically, the size of VI. And that's why we split the vertex set to many parts so that each VI is pretty small. So at the end of the day, if you can indeed find almost perfect matchings, then you are happy. But in order to find almost perfect matchings, you need the graph to be very close to being regular. And this 18 almost regularity will not do. It would only give you, say, 1/18th proportion of a perfect matching. So yeah, so this is hopefully now the entire picture does make sense. On the top, we have the matchings glued together. In the middle, we have the reservoir, and the bottom, we have the absorber. So there's still the issue why, I mean, even if G was regular, there is still the issue why would this UAbs 2 induced subgraph on that set be regular? I have not explained that. Now I'll do so now. So even if assuming that G is regular, why is this induced subgraph regular? And here's a cute trick. So that's actually not the induced subgraph we'll consider, but we'll first sample vertices from the set of vertices that are not used in absorbers. So this W is sampled from U minus X minus U abs. So sampled from the set of vertices that are not in the absorbers, and each vertex is chosen with probability 1/2. And now for each vertex in R that I want to absorb, I randomly allocate which of the two absorbers assigned to that vertex is used for each cycle. So for each R, it's a random decision. That's why I get the random chain of green and red absorbers. And now I claim that W union U abs 2 is almost exactly a 1/2 random subset. I first of all claim every vertex in U minus X is in it with probability 1/2. And that's because if a vertex is in U minus X, either it is in the chain of absorber pairs, in which case it's either with probability 1/2 is chosen to be in the first cycle, with probability 1/2 is chosen to be in the second cycle. So indeed, probability 1/2, it is in U abs 2. And if it's not in the absorbers, then it gets sampled to W with probability 1/2. So surely every vertex gets sampled to this random subset with probability 1/2. They're not exactly independent because the absorbers, if you have an absorber, either the entire gadget goes to U abs 2 or the entire gadget goes to U abs 1. But gadgets are small, so dependencies are not bad. So you can still use concentration inequality. So this random subset is as good as a 1/2 random subset. And now we're happy. If G was regular and U and X are random subsets, then obviously U minus X is nearly regular, and a 1/2 random subset of it is still nearly regular. So assuming the original graph was regular, we are now happy. We can find my Hamilton cycle on this induced subgraph, and I use the reservoir to connect certain pairs and close up a cycle. And both of our cycles will have the same vertex set W union all the vertices that appear in these absorbers union the reservoir. So that's going to be vertex set of both of my cycles. So what I need to do is explain how you deal with the case where the graph is not regular. So now let me talk about the regularization. Our argument certainly relied on the graph being regular. 18 regularity, as I said, is not enough. So we need to do something. And we proved the following lemma, which first of all makes your subgraph much more regular. But second, it also contains the vertex set of your subgraph will contain a large random subset of the vertices. So most of the known regularization tools don't allow you to control the vertex set of your subgraph. And this tool will allow you to control it because the vertex set of your subgraph will contain a large random subset of the vertices. And that will work really well with expanders, as we can see. So this is the statement. Let me just explain. So if you start with a graph that's, say, 18 almost regular, or choose your favorite constant here, it has degrees between D and 18D, and you choose a subset of the vertices with some small constant probability. Then you can find a subgraph whose degrees are all very close. They are between d prime minus log n and d prime plus log n for some d prime that's as big as the original degree. So d prime is essentially as big as the original degree. The error is now an additive log n, so very small. And crucially, your subgraph has vertex set that contains a large random set A. So we have very good control on the vertex set of H as well. Now, one thing that I should point out that is that H, the H that we obtain may not be an expander still. It contains a large random set of vertices, but it still may not be an expander according to our definition of an expander. However, what do we use about expanders? We use that a random subset of vertices in an expander is nice. And this survives for H, because H itself contains a large random subset of G. So if you now take a random subset of vertices in H, it contains a large random subset of vertices of A, which itself is a large random subset of the vertices of G. So whatever we used about expanders can be used the same way as before. So in the last few minutes, let me talk about just this regularization lemma. And in particular, how we prove it. The regularization is achieved in many small steps. And in each step, the graph will become a bit more regular in the sense that the ratio between the maximum degree and the minimum degree will drop a bit, while the average degree doesn't drop by too much. So what does one step of this regularization look like? But let's assume that the graph has degrees between d and 1 plus 10 epsilon d at a given step. And I'll make something random with it that corrects the degrees by an epsilon amount. I'll make something rather delicate, like it's a small change that corrects the degrees by some epsilon. I split the vertex set to low degree and high degree vertices. Low degree vertices are those with degree less than 1 plus 5 epsilon times d. High degree vertices are those with degree more than 1 plus 5 epsilon d. And I take a random subgraph where I delete edges and vertices randomly. If I have an edge between a low degree and a high degree vertex, I delete it with probability epsilon. If I have an edge between two high degree vertices, well, I want to decrease that degree a bit more because that edge goes between two high degree vertices. So I delete it with a bit higher probability, 2 epsilon minus epsilon squared. I do not delete edges within low degree vertices because they are precious. But I do also need to delete vertices. And I delete vertices, low degree vertices, independently with probability epsilon. So these are the three things that I do. And well, I don't really have time to go through this check, but the crucial thing here is that conditional on a vertex, on a low degree vertex surviving, its degree on expectation drops by a factor epsilon. So each edge incident to a low degree vertex survives with probability 1 minus epsilon. However, each edge incident to a high degree vertex survives with a smaller probability. So the degrees of high degree vertices will drop quicker than the degrees of low degree vertices. So the graph will become more regular. And moreover, we only delete vertices in each step with probability epsilon. So very high probability vertices survive even after many iterations. So that's why you get that the subgraph that you obtain at the very end will contain a large random subset of the original vertex set. And in the last slide, let me just give one other application. In a forthcoming paper, we developed variants of this regularization lemma. We needed to work a bit harder to obtain these applications. They don't quite follow from the version I stated before. And one particularly nice result that we prove is that almost regular graphs contain fully regular subgraphs with essentially the same degree. So if you start with this, say, 18 almost regular graph, you can find in it a fully regular subgraph with essentially the same degree. And that's the formal statement is here. If your degrees are between d and lambda d, then you can find in your graph an R regular subgraph with R of the same order as your original degree. And yeah, so, well, one thing I will say is that this is going to be a useful tool for regularization problems. There are many famous important tools for getting almost regular subgraphs. One very well-known example is the Erdős-Simonovic regularization, which gives you an almost regular subgraph. It's widely used in Turan type problems. You can now use our theorem to actually get a fully regular subgraph, and you don't have to pay anything in addition. So it's going to be definitely very useful. And also, it does significantly improve a celebrated result of Alon, Friedland, and Kalai. Their results stated that if you have a graph whose degrees are between d and d plus lambda, then you can find an R regular subgraph with R same order or same order as d. And our new result allows you to replace this rather restricting condition, d plus maximum degree being at most d plus lambda by maximum degree being at most d times lambda. So applies much more generally. I should say that our proof of this last theorem does rely on the Alon, Friedland, Kalai result itself. So certainly their proof is still very important, but it's certainly the case that our result vastly extends their result and makes it even more applicable. And that's all I had time for today, and I'm very happy to take questions.
Thank you, Oliver. So, right, you can unmute yourself and ask Oliver questions if you have one.
So in this last theorem about the fully regular, do you need to assume that d is at least some power of log or something?
No. So this is the really nice thing that you don't. It works for any d, extremely sparse, and that yeah.
What about
that's
this
one of the very
Pyber, Rödl,
things.
Szemerédi example? Like,
well, that example is not. I mean, that example does not satisfy the conditions.
Oh, I see. Yeah. Okay. Got it. Yeah.
So this is a tool for getting from almost regular to fully regular.
Right. Okay.
Thank you.
Thanks.
More questions?
Hi. So, is there any chance, for example, if the host graph is itself certain expander, and then you can find a regular subgraph which expands also well?
Well, I mean, okay, so our result does give this in a weak sense, but if you want to say that you start with an epsilon s robust expander and you want to find in it a regular subgraph, which is an epsilon prime s prime robust expander, we are not aware of such a thing. And I mean, such a thing would have been useful for us. But we weren't aware of such a thing. So that was part of the reason why we needed to invent this new
Yeah.
regularization. I mean, certainly the regularization techniques I'm aware of, they don't really allow you to control the vertex set of your subgraph. So that was one of the big issues, that the vertex set, I mean, particularly this Alon-Friedland-Kallai, for example, what you get is a vertex set. You don't have any control on it because it's an algebraic tool. So there are other regularization techniques, but they don't seem to allow you to control the vertex set.
Thanks. But is there any evidence that this might not even be not true, or?
Yeah, good question. Yeah, we are not aware of a counterexample.
Okay, thanks.
More questions? So if not, let's thank Oliver again for a very nice talk. We can stop recording now.